Hello everyone, welcome to a fresh new lecture on the topic Wavelet Transforms 1. This is Dr. Anirban Dasgupta and let's get started. So to introduce wavelets, let us first understand that what are the limitations of our short-term Fourier transforms. So the first is fixed time frequency resolution. What does that mean? So in our STFT, the time frequency resolution is fixed because the window size is fixed. So if we have a larger window, say the window is defined in terms of your n, the signal length or the window length rather. So here if I have a larger n, then typically we are computing n point DFT, and higher the value of n, better is my frequency resolution. Why? Because I am able to represent more number of frequencies for that specific window. But the time resolution gets poor. Why? Because the larger the window, I am not able to localize that exactly where my event has occurred. For example, if my window size is 0.1 second, then I know that in that 0.1 second or a fraction of a second, that event has occurred. But if I am analyzing in a window of say 5 seconds, that's a big window. So anywhere in that 5-second duration, these frequency components are present, but exactly where, it's not localizing in a very precise manner. So the time resolution will be poor. So this trade-off makes STFT difficult where both high frequency and low frequency components are present in the signal, because each will require different resolutions. The second is capturing sharp transients or discontinuities. Now in many signals, say for example, say a signal is suddenly changing like this. So if you need say sinusoids, maybe you have to use a lot of sinusoids to represent this. So this is one sinusoid of a specific frequency, then another sinusoid which is of higher harmonic, then another fast varying sinusoid. So a lot of components will be used to approximate this kind of sharp change in the signal. And this, since this sinusoidal basis, which is the basis for our short term Fourier transform, this is a smooth signal. So it is very difficult to capture the sharp discontinuities. Like you will need lot of components from a low range to a high range to capture this kind of discontinuity. And the very good example is our square wave, where we will ideally need infinite number of sinusoids to approximate this square wave. So this brings us to the concept, just I am giving you a hint, that if my analyzing signal was instead of a sinusoid, if it was something like a square wave, then this kind of a signal is easier to analyze with less components. Now to understand wavelets, what is a wavelet? Let us try to first define it. So a wavelet is a small oscillatory function psi of t that is localized in both time and frequency. What does it mean? So sine, which is the basis, sine or cosine, sinusoidal function, which is the basis for Fourier analysis, is not localized in time. It is present everywhere in the time domain. But wavelet is a function which is of short duration, that is, it has limited duration, and that is the reason why you can capture some events which are of short-lived duration. Has an average value of 0, this is same for sine also, and non-zero norm. So the main distinguishing factor is that it has limited duration, this analyzing function, and this function is usually termed as the mother wavelet, because from this mother wavelet we will derive other wavelets. Now this mother wavelet, say I have any signal which is varying from any duration. So if I have a short lived signal which is I am calling here wavelet, so I cannot say I have a signal which is varying like this, and I have a signal which is like this, and this I called as a wavelet. So I cannot, if this is having a period, not period, but duration of say 0 to say 10 seconds, and this signal which I am going to analyze is having a duration say 0 to something like 50 seconds. So, just with this signal, without using any operations on this, it is difficult to analyze throughout the analyzing signal or signal which is to be analyzed. It is very difficult to get that. So, mother wavelet is scaled. Scaled means if you see, these are faster than the mother wavelet. So, I have to shrink them, whereas there can be cases where the mother wavelet is dilated. So, I have to dilate the mother wavelet. So, that is the meaning of scaling. And then shifting, like I will analyze for this region, then I will shift it, analyze for the next region. So, typically analyzing with wavelets means that I have a waveform like this is called a wavelet, and I will shrink it or dilate it, and then I will translate this version and the dilated or shrinked versions to obtain this original signal x of t, and this wavelet is called psi of t. So, I will analyze this x t using psi of t, its scaled versions and its translated versions, and translations of the scaled versions. And by this manner, I can capture the various aspects of the signal across different time intervals and frequency ranges. So, this is the basic difference. So, this is a sine wave, and you see the dots, which mean it is ranging from negative infinity to positive infinity. Whereas, our wavelet here, this is dB10, the Daubich's wavelet series, is having a finite support, and other than this range, it is all 0. So, say this is a Daubich's wavelet. Let us not name it as Daubich's right now. Say this is a wavelet, and it satisfied all the 3 norms, that it has limited support, it has 0 mean, and it has non-zero norm, and I call this phi naught t. Why phi naught? Naught here means that this is the original mother wavelet where I have not done any scaling or translation operation. Now, if I translate this to 1, that is, if I delay this by 1 second, so this is my resultant waveform. If I dilate this, that is divide by 2, then I get this waveform, and similarly I can translate the dilated version and I get this waveform. So, in simple terms, let us assume that a signal is a sum of these 4 wavelets taken into equal proportion, that is 1 time phi naught of t plus 1 times phi naught of t minus 1 plus 1 time phi naught t by 2 plus 1 time phi naught t minus 1 by 2. Then these are the wavelets which are the analyzing functions, and each are having a coefficient of 1, and this is the wavelet analysis or the basis of wavelet analysis. And how these analyzing functions are obtained? So, this is the notation phi a b of t is 1 by root mod a and phi naught t minus b by a. So, t minus b here is the translation, how much in time I am shifting the signal, and a is my scaling. So, what is a scaling function? So, scaling function is different from a wavelet function, and a scaling function is typically used to define the low frequency components of the signal. Typically, it is called trend in the signal, and this is often called the father wavelet. So, we have a mother wavelet, we have a father wavelet, and then we can scale and translate each mother wavelet and father wavelet and do the linear combinations of these, and that will result in the original signal. Or wavelet analysis assumes that my signal can be decomposed into the linear combinations of father wavelet, mother wavelet, and their scaled and translated versions. So, in the context of multi-resolution analysis, so scaling is associated with a space, and I call that space Vj, and this is basically a subspace of the function space L square r. What is L square r? L square r is the set of functions which are square integrable. So, what does this Vj mean? So, Vj is a space. What is a signal space? If you know what is a vector space, so vector space means if I take any two vectors from that space, do a linear combination of those two vectors, then the resultant vector will also lie in the same space. Similarly, a signal space is a collection of signals where if I pick any two signals, do a linear combination of them, the result will be in the same space. So, if I say Vj is a space, that means that if I take any two signals from this space Vj, do a linear combination, the result will be in the same space. And this Vj's form a nested sequence. Don't worry if this is sounding complicated, we will analyze this slowly. So, here Vj is a subset of Vj plus 1 for all j. Let us take j equals to 0. That means V0 is a subset of V1, is a subset of V2, is a subset of V3. And what is V0? So, this phi t, or if I can also say phi naught t, phi naught or phi t, it is typically the same thing. Some books will use the notation phi 0, some use phi t, some use phi 0 t. The concept is that this is the scaling function or the further wavelet. So, all the translated versions and their linear combinations will form a signal space. So, phi naught t, phi naught t minus 1, similarly any alpha times phi naught t minus b, all these translations and their scalar multiplications will make a set of signals which is denoted by this space V naught. Similarly, what is V1? V1 is the scaled versions of phi naught t, and that is given by A. So, V1 is typically, you can consider this as phi of t by 2. Similarly, V2 you can consider as phi of t by some other scale, something like that. So, these are forming a subspace, because if anything which is analyzed in V0 will be also present in V1. So, V1 is a superspace which contains V0. Similarly, V2 is a superspace which contains V1 and so on. Similarly, you can also have V of minus 1. So, this is what I was talking about, that Vj is a linear combinations of translations and dilations of phi of t. So, the V0 is the translation of the scaling function phi t, which I just explained now, and V1, V2 will be capturing increasingly finer details by dilating our phi t at different scales. So, now coming back to the wavelet function. So, similarly, like our phi, we can also do translations and dilations of our mother wavelet, which is psi naught. And wavelets are basically difference or detailed approximations at different scales. So, this is denoting the high frequency content, whereas the further wavelets or the scaling functions are denoting the low frequency components. Now, like our scaling functions form the face V, our wavelet functions will define the spaces Wj, which are associated with high frequencies at level j. And one interesting factor is that our Wj space and our scaling function spaces Vj will be orthogonal spaces. And this is what I told. So, Vj's will capture the low frequency and Wj will capture the high frequencies. So, if we have the Cj's and Dj's as our approximation and detailed coefficient respectively, then this is how our analyzing function will look like. So, V1 is j equals to 1, V2 will be j equals to 2. So, it will capture all the respective scales and the linear combinations at each space. Now, pictorially if you see, it will be clearer. So, if we consider this circle as the linear combinations of the functions that I called psi naught or psi t, and its translated version and their linear combinations. So, we can define another circle which is V1, this is V0, this is all linear combinations of psi naught t and its translations. So, V1 is a linear combination of psi 1 t, psi 1 t means here it is the scaled versions, that here I say this is by 2 and this is the linear combination of all this. Now, if you see, so there are some signals in V1 which is not present in V0, which is this annular space. So, I can call this space as W0. This may not be a signal space, but consider that this is the set of signals which is forming the annular region. So, this whole disk if you see, that is V1, but this annular region if you see, that is W0. And likewise, I can create my V2, which is the big yellow disk, and the difference space which is forming or which is excluding this V1 is my W1. And similarly, I can have W2, which is this annular space, gray space. And if you see the whole disk as such, it is my V3. So, this is V1, which is this space, this whole disk, the pink disk. So, which is consisting of the union of my V0, which is the bluish disk, and the W0, which is the annular pinkish space. Similarly, V2 is the whole yellow disk, which is comprising of V1. Now, V1 is this pink space, and then W1, which is this annular ring, and this is the recurrence relation. Now, we have got a good amount of idea about what are wavelets. Now, we will talk about Haar wavelet, which is the simplest possible wavelet. Now, Haar was not defined as a wavelet. Dr. Alfred Haar typically gave the idea of this scaling and this approximation and detail function in the way back in 1909, and there the concept of wavelets were not present, unless in the late 70s or probably early 70s, Ingrid Daubechies, Dr. Daubechies gave the solution to wavelets or the term wavelets to his famous discovery or rather formulation of Daubechies wavelets, and Haar wavelets can be taken as a special case of Daubechies wavelets, which is dB1. So, what is the Haar scaling and wavelet function? So, the Haar scaling function is this. So, it is having a value of 1 from 0 to 1 and it is 0 otherwise. And what is the Haar wavelet function? It is having a value of 1 from 0 to half and minus 1 from half to 1 and it is 0 otherwise. Now, first thing is that initially when I said say we want to analyze square waves, and if I use sinusoidal basis, it will take infinite number of sines and cosines. But if we analyze with this function, then it will be much easier because we have these sharp boundaries. The second thing is that if you see, if this is my phi t and if I take a signal which is just a compressed version of this, like if this is my psi t and if I take a signal which is just compressed, say psi of 2 t, and if I do a subtraction of these two signals, what I get? So, typically here this portion should be, but there is also a scaling because there is 1 by mod a kind of a thing. So, technically you will get this as a difference kind of a signal. So, in simple words, this is like averaging out. If you convolve with this signal, you are averaging a portion of the original signal, whereas if you convolve with this signal, so this is basically adding this part and then subtracting them. So, this is like a difference of the signal. So, this is capturing the high frequency zone and this is capturing the low frequency zone. So, this is what I was talking about. So, if I scale this function, so this is my Haar wavelet. So, if I scale the wavelet, so what I get? I get this is at a scale of 2. If I do at a scale of 4, that is dilation of 4, I get this waveform, and if I dilate at a factor 1 by 2, that means it is shrinking it. So, this is the waveform, and by using different scales and translations, you would be able to analyze any signal, of course with the linear combination, that is each of these wavelets and their shrunken or scaled versions will have some weights, and those are your Haar coefficients. So, now talking about the continuous wavelet transform or CWT. So, the CWT is given by the formula this, and here I am talking about a discrete time sequence. So, this is convolving this with the different wavelets, and here why it is continuous? So, it is continuous in scale and translation. So, I can use any factor of A and B and then translate this. So, what is the importance of CWT? CWT, the scale factor is the major factor which is determining the frequency content of a signal. So, if your scale factor A is like, if it is small, that means it is determining high frequencies because they are compressed wavelets, and here you get good time resolution because you have smaller versions. So, these are smaller versions, so picking up highly varying or fast varying signals, whereas large values of A are relating to low frequencies because these are kind of dilated versions. So, capturing slow changes in the signal, and of course, this is the wavelet functions scaled versions. We will also have the scaling functions scaled versions also, or the father wavelets, and in this manner it will give you a continuous mapping of the signal's time frequency content, and this is very useful for non-stationary signals. This is I have already discussed while introducing time frequency analysis. And similarly, like the forward transform, we should be also able to recover our signal from the coefficients, and that is given by this relation, which is also called the inverse CWT. And here we have C naught, which is our normalization factor. And one thing is to be noticed that these normalization factors or all these scales are selected such that the energy content or the Parseval theorem is valid. Our energy content is both same in the wavelet domain as well as in the time domain. So, likewise, so far I just gave you an example of the Haar. Similarly, there are other wavelets which are available, and they are sometimes or often called wavelet families because there is not a single wavelet, but a family of wavelets. So, Haar we have already discussed. I also named Dobbich's, and because of Dr. Ingrid Dobbich's, this Haar as a wavelet got the name. Then there are wavelets like simulets, which are variations of the Dobbich's. There are quafflets, and there are biorthogonal wavelets, and there are many such wavelets like modlet, and you can create your custom wavelets as well, which follows the rules of wavelets. So, the best thing is that whenever you are analyzing a signal with wavelets, you should try all the wavelets and see which is very nice for your specific signal or specific application, because each signal will have a specific pattern which may be captured by a specific set of wavelets. So, just a pictorial representation of these wavelets, like this is Haar already introduced. These are quafflets, and you see the pattern and how this quafflet 1, 2, 3, 4 and 5 are evolving. Similarly, the Dobbich's wavelet family. So, these are the families. So, we have simulets, and this is how simulets look like, and this is the biorthogonal wavelets. So, these have been obtained from MATLAB, So, what is this CWT algorithm? So, the first step is to select your mother wavelet. Now, you can define your own custom wavelet also, but that is a challenging thing. Better you use a standard wavelet which is available. The next is you have to scale your mother wavelet by A, and then you have to shift it by B, and then you create such filters, and then you have to convolve them with the signal, and your each convolution will result in different outputs which are denoting your time and frequency aspects of the signal. And when you repeat for different values of A and V, that is your time frequency representation of your signal. So, we will stop here and we will come back to further on wavelets. Thank you so much.